Hello, everybody. My name is Rahmani. I'm a PhD student at the Laboratory of Applied Photonic Devices at EPFL based in Lausanne, Switzerland. Today, I'm going to talk to you about multimode fiber projection with machine learning. Uh, as you know, we have two categories of fibers. One is a single mode fiber in which you send your information bit by bit. So basically ones and zeros, and then you are able to transmit whatever information you want to send. And this is as opposed to the second type of fibers that we have, and we call the multimode fibers, in which, as the name suggests, a lot of modes could be simultaneously sent through the fiber, and then you can have this massive set of information being sent to the fiber at the same time, which gives you a large throughput, basically. But then the drawback of the second system of multimode fibers is that you get this unwanted detrimental effect of modal dispersion, in which an image that you want to send to the fiber gives rise to this scrambled pattern at the output of the fiber, which we refer to as speckle patterns. And this is because of these several modes that are propagating through the fiber. They have different velocities, and they basically propagate with different speed. So then when they're gonna meet at this output of the fiber, the phase accumulation of different modes is different, and then you have this this modal mixing at the output. So if you want to send an information to the fiber and then have a particular image at the output, we really need to think about something, an approach that is able to compensate this effect. And so that would be basically the main topic of this presentation. So this is my outline. At first, I'm going to talk about different methods that's been studied and investigated over the years for image transmission or image reconstruction to the fibers. And then, of course, I'm going to talk about our approach here, which is using neural network for image reconstruction or image transmission. So as you can imagine, the image propagation through multimode fiber has a really rich history. So the first demonstration of image transmission dates back to the 60s in the work that was studied in France. And then after that, so a plethora of approaches was proposed by different scientists and different groups around the globe for thinking about a way to compensate the modal dispersion. And you can imagine the works of pioneering work of Yariv, in which so he wanted to take advantage of the nonlinear effect using Cliff Star, and using that effect for phase conjugating the information at the output. So these modes, they're propagating to the fiber, and then each mode has different phase at the output. So using this nonlinear effect of a crystal, you can simply phase conjugate the output field and then resend that information to second fiber, which has exactly the same characteristic as a first fiber. So then the modes will propagate and then compensate the accumulation of phases, and you have your original image at the output of the second fiber. Then there are works around the iterative approaches using special light modulators, in which special light modulator was used to iteratively trying to focus, usually spot, at the output of the fiber. And then so you basically, with these approaches, you are limited to only projecting simplistic, most simple images at the output, basically. Then at the end of this bag of approaches that you can imagine, it was like the most common, and the state of the art is nowadays the transmission matrix method, in which using holography for measuring the phase at the output of the fiber. You send a bunch of images through the input of the fiber, and then measure, as I said, the complex field, the phase, using holography at the output. And then with that, you are able to construct an input-output relationship and measuring basically a matrix, if you will, to relating this input to the output. Then if you want to send, you want to have a particular image at the output of the fiber, you just invert the matrix, and then to see what input you should send to get your desired output. Of course, this has its nuisance that I'm going to talk about, that would encourage one to investigate further approaches that makes you not really needing to measure the phase. So if you use this matrix approach, you can send arbitrary images at the output. But again, the problem that we want to focus on here is image propagation without phase measurement. So we have a specialized modulator, we have this fiber, and we have a screen or camera. Without measuring the phase, without measuring anything more than just the amplitude information at the output in the camera, we want to send arbitrary images at the output. And of course, you can think of using neural networks for that. This is the topic, of course. And then, but I want to make a difference between image propagation and image transmission. So we did before using neural networks, which are published in Nature Life Science, for image reconstruction, meaning that if you send particular data set to the fiber, you get scrambled images at the output. But then using neural networks, you can train to reconstruct from the scrambled information at the output. And we showed that before. So this is image reconstruction. A similar line of works have been done using other types of scattering medias, but of course, so they derive the same approach for image reconstruction. But the problem here for image propagation, so you want to control the output. You don't want to guess what the input was. Just want to send the output. The problem here is you don't know the ground truth for a particular image to send to obtain the output, to send to the fiber and get the output. So this is the problem here. You cannot use neural network in the simplest way as supervised learning to relate the input to the output, because you don't know what ground truth would result the output. You don't have basically the ground truth for that. So if you don't have that ground truth, then you have to use this particular type of neural networks, which are comprised of two sets of networks. We call them G and D. So the D, which is the second network, emulates the input-output of the fiber. And the other network, which is G, emulates the reverse pass. So I'm going to talk about it in a bit how they're trained, but for the time being, just as an abstract, when the G and D networks are trained, then you ask a network, basically the reverse model, what the image that you want to have at the output. And then if it's converged, these two sets of two networks are converged and the loop is closed, then the G network gives you this pattern that you should send to obtain the particular image at the output. And if indeed you do that, then you send this control pattern, the images that G gives you, to the fiber, and you can have the same image at the output. So how we are training our system here is that because you initially don't know what input to send, you send some random images to the fiber to get the input output. So random image, random output. Of course, the output looks specklish, doesn't look the kind of images that you want to have. And then you train your D model, the forward in model, based on that. And then in the backward, and so you train your D. And then when D's train, you fix that, and then you train your G. So you ask G to give you a particular target control patterns for a particular target outputs. And then G initially doesn't know what the relationship, but using the information of D, G gradually learns to give you the particular control pattern that you really need to have. So once the training is done, you simply can send the control patterns that the network G gives you to the system here being the fiber, and then you have your output at the camera side of the fiber. So you can think that you can redo these input-output or G and D training for several times if the quality of images that you want to at the output fiber is not satisfactory. So you can repeat the back and forth training of G and Ds for several times, and you can see there's a fidelity here. Fidelity, for performance, we measure the correlation of the image that you really see at the output and the thing that you want to see at the output. And then you see as you can do several times, and then your quality of images get better. So we did that. We trained our network with particular images of MNIST, the Latin alphabet characters, and then we for several wavelengths, and we showed that it is indeed possible to train a network to project particular data set at the output, and then using that network, you can send arbitrary information and project those information at the output. And then not only simplistic types of images, you can project any kind of information at the output of the fiber. So with that, I want to conclude this presentation. So we propose a particular architecture for neural networks in which, without measuring the phase, you can project any images at the output and obtain, I want to emphasize that, the same quality of images as you would get in a transmission matrix, which measures the phase too. You can think that you can use this approach for other disciplines in which you don't measure all the output, but you measure partial measurement. I want to thank my professors, Christoph Moser, and my other professor, Dimitri Psaltis, for this work, and I wish you a good day, or not, wherever around the globe you are. Thank you.